When you use your computer or connect to a network, you just expect it to work, right? But how do we actually prove that it will always work correctly? And maybe more importantly, that it'll work fairly for every single task it's juggling? Well, we're about to dive into a really powerful logical tool designed to do exactly that. Okay, to really get this, let's think about it like this. Picture a huge, endless library. But instead of books, every single shelf, every aisle, it all represents a possible future for a computer system. Every decision the system makes is like taking a turn down a new, branching corridor. So here's our game plan. We'll start out in our logic library. Then we're going to run into a tricky problem with this idea of fairness. After that, we'll meet our solution, which is ECTL+. We'll see how it actually works, and then we'll figure out exactly where it fits in the grand scheme of things. Right, so how on earth do you navigate an infinite library of possible futures? Well, computer scientists use these special languages called temporal logics. You can almost think of them like a GPS for verifying exactly how a system is going to behave over time. Our journey's going to start with a language called Computation Tree Logic, or just CTL for short. It's basically a way to describe what a system can do by exploring every single possible branching path in our library of futures, kind of like following all the branches of a giant tree. Now, with CTL, we can ask some pretty direct questions. In our library analogy, that might be something like, hey, is there at least one path from where I'm standing now that eventually gets me to the front desk? Or you could ask something bigger, like, no matter which path I take, will I always be able to find an exit? It's fantastic for these kinds of fundamental checks. But this is where we hit a snag. Because what happens when the rules get a little more complicated? Turns out, these simple questions just aren't enough anymore. Yeah, what if we need to ask something a bit more nuanced? Something that has to account for certain conditions being met again and again and again for a system to be what we would call fair. And that brings us to this really key idea: fairness constraints. These are basically rules we put in place to make sure a system isn't just correct, but that it's also playing fair. Think about your operating system juggling a bunch of different programs. A fairness constraint is what makes sure it can't just ignore one program forever. It has to give every process a fair shot eventually. And this right here is the perfect way to see the difference. A simple CTL question is it possible to borrow a book? Simple enough, right? Yes, but a fairness question is way more complex. Is it possible to keep borrowing books, but only as long as I follow the fair rule of always returning them on time? See the difference? CTL really struggles with that kind of layered, conditional logic. It just wasn't built for it. So to tackle this very problem, researchers developed a more powerful, more expressive logic. And this, my friends, is where ECTL Plus makes its grand entrance. ECTL Plus. It stands for Extended CTL Plus. It's a type of temporal logic that was specifically designed to be, well, strictly more expressive than the original CTL and its first extension, which was just called ECTL. It was basically built from the ground up to handle exactly these complex fairness situations. So what's the big superpower of ECTL Plus? It's all about handling complex combinations of fairness rules using simple logic you already know, like and, or, and not. This lets us get super specific. We can say a system is only fair if, say, process A gets resources infinitely often and process B does not get stuck in some loop. That kind of nuance, that's exactly what was missing before. Okay, so ECTL Plus is more powerful. We get that. But how do we actually use it to check a system? Well, the method they came up with is just as clever as the logic itself. The secret sauce here is something called the clausal resolution method. The best way to think of it is as the engine that takes our complicated fairness questions and just systematically works through all the logic to find a clear, definitive yes or no answer. So here's how that process works, in a nutshell. First, you write down your fairness question as an ETL plus formula. Second, that formula gets translated into a standardized format, this normal form. Third, an automated system starts applying these logical resolution steps. It's a little bit like solving a Sudoku puzzle, just logically, step by step. And finally, if the whole puzzle can be solved, bam, your property is verified. Now, to really appreciate what makes ECTL Plus so special, it helps to kind of zoom out and see where it sits in the larger family of these temporal logics. It's all about a trade-off, a balance between how much you can express and how practical it is to actually use. You can see this clear spectrum here. At the basic end, you've got CTL for those simple properties. ECTL comes next, it adds some limited fairness. Then way up at the top, you have this beast called CTL star, which is incredibly powerful, but honestly, it's often way too complex to work with efficiently. And look, right there in the middle, giving you high expressiveness, is our hero, ECTL+, with its killer feature, those awesome Boolean fairness combinations. And that's why ECTL Plus is such a big deal. It just hits that perfect, practical sweet spot. It gives us so much more power than the simpler logics, but it does it without the crushing complexity of the most powerful ones. The magic really is in that balance. It's about having that richer expressiveness while still being manageable for automated reasoning. And that second part is everything. It means we can actually build automated tools, like that resolution method we talked about, that can check these complex fairness properties efficiently in the real world. So here's the bottom line. ECTL Plus is this specialized tool that lets us go way beyond just asking if a system is correct. It lets us actually prove that a system is fair, making sure that no single process gets starved for resources or just ignored forever. And that is absolutely vital for the reliable software that, let's face it, runs our entire world. And that kind of leaves us with a final thought to chew on. As the systems we all rely on become almost unimaginably complex, our tools for proving they work have to evolve too. The question isn't just, does it work anymore? The real question we all need to be asking is, does it work for everyone, fairly?